Okay. Thank you, everybody, for coming back and joining us. And appreciate your patience with the technical difficulties. This webinar is welcome to performance of road bases using Foundry sand and crushed concrete blends. Our speaker today is Mr. John Dingledine, Vice President of Soils and Materials Engineers. He's going to lead the webinar. John is a professional engineer who has designed multiple highway projects using Foundry sand and other recycled materials, and is the lead engineer on this research project. The project results will show that blends of Foundry sand and crushed concrete can meet state DOT specifications and perform as well as or better than conventional aggregates and road bases. This work was completed thanks to a grant from the U.S. EPA Region 5 and was directed by the guidance of Elizabeth Olenbush of EO Associates. Should you have questions, there is a box in the lower right-hand corner where you'll be able to type in your questions. We appreciate your attendance today and, again, your patience, and I will hand it off to John. Thank you.
Well, thank you for attending today's webinar. We'll give this another start if I can regain my composure here. The topic today is on field demonstration of blended base courses containing recycled concrete aggregate and Foundry sand. Just like to make a few acknowledgments that Michael already made, but we'd like to thank the EPA for granting the project. It was sponsored through AFS First. It was administered by Elizabeth Olenbush, who's put most of this product together. The project was provided by the village of Cuyahoga Heights. Paul Day is the city engineer there, and he helped coordinate between their project team and our material suppliers. He also helped schedule for the time of the project when we could show up and do the various aspects that we needed to complete. The materials and technical support were supplied by Kurt's brother and John Kurtz in particular, and the field and laboratory services were provided by SME. Highway administrations are moving more and more to construction of green highways using more recycled materials. By combining two of the largest recycling streams in the region, recycled concrete and Foundry sand, a successful blend of materials can be produced for roadway base and other uses. The project objectives were to enlarge the market for recycled materials, to compare the performance of a recycled concrete Foundry sand blended aggregate blended to an ODOT 304 gradation with that of the standard ODOT 304 crushed limestone base, to expand business for recycled material generators, to generate data to help develop future standards and specifications for the use of recycled materials, and to develop and disseminate a case study. Our project was a Rails to Trails project located in Cuyahoga Heights. The location is a suburb of the greater Cleveland area. It's located just north of Interstate 480 and east of Interstate 77. This aerial photograph shows the old railroad subgrade with the track still on it. Our project area, our demonstration area, is the area marked in the red. The Cuyahoga Heights maintenance garage is located here. After this picture was taken, they had constructed another maintenance building, and in 2012 they constructed an access road off of our main entrance into the facility here. This plan view shows our actual test section areas. This first section here is the standard ODOT 304 limestone. The second section here is the recycled concrete Foundry sand aggregate, and we had a third section with a different material in it. As part of the original study, there were soil borings conducted along the railroad right-of-way, and in addition to that, there were several static cone penetration tests that were probed into the subgrade to give us a better understanding of the relationship of the subgrade to the natural subgrade. As part of the project, we also installed two lysimeters located under each of the primary pavement sections, and they were called lysimeter A and lysimeter B, and we collected groundwater flow through the base course and did analytical testing on those water samples. This is just a view looking south back towards the main road. Our crushed aggregate limestone is in the first section. The second section here is our recycled concrete foundry sand blend. These arrows are pointing to the approximate locations of where the lysimeters are placed. The subgrade slopes from the right side of the photograph down to the left. And then along this left edge is constructed a French ore collection drain to help keep the base course permanently drained beneath the pavement. Our subgrade was a railroad ballast that was placed in the early 1900s. Back at that time in the greater Cleveland area, they used a lot of cinders and slag mixed with coal and other building material. This profile here is fairly standard throughout the section. There's about 5 feet of this fill, and it's placed over a soft to medium consistency clay. Generally, the fill material was dry. We have not seen groundwater accumulating in the base over the top of the subgrade. Static cone tests revealed that we have an upper layer here, which is the fill, and it shows a nice granular crust by the cone resistance, followed by a weaker profile for the clay. Generally, these cone resistance numbers, when they're 20 or above, you would assign just a basic bearing pressure of about 2,000 pounds per square foot for this material. The project had a design pavement section that we had to incorporate into the study. It consisted of 10 inches of asphaltic concrete, which was consisted of the surface intermediate layers and the bituminous base. This was placed over 10 inches of ODOT 304 crushed limestone as specified, and in our situation we kept the base course thickness uniform throughout the test sections. With the ODOT section here, it has a calculated equivalent structural number of 5.08. Just keep this number in mind as we get into the falling weight deflectometer test later on. We'll compare that to the design number. We did several laboratory tests on the different materials that are in this project. Included the subgrade, the fill cinder material. They had a low CBR of 2. Had a high percent passing the 200 sieve, so a 23%, which is predominantly a silty material, not clayey. It's a relatively light relative density of 101 pounds per cubic foot and a optimum moisture content of 18%. We didn't run a lot of other tests on the recycled concrete other than an initial gradation and a fines content so that we could take the recycled concrete and break it into different constituents and blend it with the foundry sand. Our foundry sand material had a CBR value of 18, 9.5% passing the 200 sieve. Typically with foundry sands in our area, this number is usually around 2 to 3%, but the source we were using for this project was slightly higher. It also had a little higher maximum density than normal, which was normally about 109 pounds, so we had a little higher density, and our optimum moisture content was slightly higher than typically what we see for a lot of foundry sands. Our blended aggregate, the 304 recycled concrete with the foundry sand, had a CBR of 34, P200 of about 8%, density of 119, with an optimum around 13. When you compare this to the crushed limestone, it had a CBR 55, P200 of 11%, slightly dirtier material. Maximum dry density was quite a bit higher at 141, and an optimum moisture content of 6%. This is just a gradation curve for the subgrade material showing that it is a well-graded cinder material that is predominantly granular. This curve is for the foundry sand constituent. It shows that the foundry sand material is poorly or uniformly graph-graded material with about 10% fines in it. Again, typically our foundry sands run cleaner than this, but in this project we're using a certain source of material. The final combination of materials shows that the ODOT gradation with the bounds, the upper bounds and lower bounds for the gradation are in red. The yellow or orange curve here is the ODOT limestone material, showing a pretty well graded material with less coarse aggregate in it than what our blended material has. So our blended material had a little bit more top end sizes in it and was cleaner than the standard 304 material that we used. In preparation for the road bed, the railroad ties and rails were removed. The coarse ballast in the top of the pavement was stripped. The subgrade then was heavily proof rolled and then compacted with a vibratory drum roller. The proof roll was stable under the loaded aggregate trucks, but you'll see later that the compaction or density tests are lower than what you might expect. Once the subgrade was stable by proof rolling, we cordoned off our sections, installed the lysimeters, and then placed our base course materials. Once the base was placed, we used a smooth drum vibratory roller to compact the materials to obtain their final densities, and then placed the asphalt layers over the top of them and tested the asphalt. The compaction results are as follows. The subgrade material, the cindery material only achieved a compaction of 81%. You can see that sort of optimal moisture content was at 18%, and so we were 2% over optimum, which makes this material a little bit more difficult to get greater densities. But like I mentioned earlier, the subgrade was stable under the proof rolling with the loaded tandem axle dump trucks. The limestone section, we obtained 95% compaction, and on the recycled concrete aggregate, 99% compaction. The additional rolling on the limestone did not improve the density any greater, so we reached a maximum density with the size of equipment that they had on site. Once the pavement was completed, and this paving project was completed in December of 2011, we ran falling weight deflectometer tests on the pavement on both the inbound and outbound lanes. The inbound lane is called lane 1, and the outbound is lane 2. Lane 1 is closer to this lower edge of the asphalt where the curb drain is located. Right now the position of the truck is really sitting over lane 2. You can see on the falling weight deflectometer equipment you have sensors along this bar that are picking up deflections as the test is conducted. This is just the back of the deflectometer showing the foot that imparts the load into the pavement. This is the weight that is lifted and dropped, and then we have another sensor down here for checking the thermally the temperatures of the pavement at that time. Right now the truck is set up on the inbound or lane 1. You can see its relative position to the edge of the pavement or where the curb drain is. Falling weight deflectometer imparts a load into the subgrade. That signal is sent down through the subgrade and is picked up through the deflections of these sensors along the trailer here. The maximum depth of this heavyweight deflectometer is capable of sensing things down to about 15 feet. From that, the data can be analyzed and the pavement materials or sections can be removed from the overall data. This presents the data after our test in December of 2011. This data is not temperature corrected to 70 degrees. It's the original temperatures that the pavement was at the time of the test. You can see the upper number here plots lane 1 and lane 2. You can typically see on these curves that lane 1 numbers are lower than the lane 2 numbers. We think this is due to the proximity to the edge of the pavement and also to the trench drain that runs along that edge. The average structural number for the limestone paving test section was 4.28. whereas the average structural number for the recycled concrete aggregate foundry sand blend was 4.32. Rounding these off, you can see that the structural numbers were essentially equivalent. This demonstrates that initially the recycled concrete isn't working or functioning as a structural part of the paving section as well as the limestone base material. We came back in July of this year and ran another falling weight deflectometer test, and it was so this was after 2 winter cycles on the pavement section. This graph just really plots, there's 2 separate figures I'm going to show you here, and this one is for lane 1, temperature corrected to 70 degrees, so the 2001 data is corrected to the temperature that the 2013 data. You can see that the structural number for the limestone started at about 4.04. There was a slight loss in structural number over the last 2 winters on this section, whereas the recycled concrete foundry sand blend had a just a slight increase in the structural number over this two winter period. And this is for lane 1. This is the lane that's by the outside edge of the pavement. On lane 2, you see similar results at the 2013 numbers for the structural number are decreased from what they were in 2011. Again, the average structural number for the paving sections for both lanes was 4.55 for both the recycled blended material and the limestone, but you can see that there was a slightly greater decrease in the structural number for the limestone section over 2 years as opposed to the recycled concrete foundry sand blend material. It shows that comparatively that both these materials are functioning as you would intend. The computed structural numbers from the field tests are slightly lower than what the design structural numbers were by calculation, but you can see they're in good agreement with each other. Just in summary, the structural numbers between the 2011 and 2013, this is the averaging of both lanes together. You can see that in 2011 that the structural numbers were very similar, that over a 2 winter cycle that there was a decrease, slight decrease in the structural number, but our limestone section really decreased more than what our recycled concrete foundry sand aggregate did. As part of the study, we collected water samples that in our lysimeters, the groundwater that flowed through the base course. The lysimeters are located beneath the pavement in this area. We have a collection tank just outside the pavement that we can insert a hose into and pump the leachate out of our containers. Once the samples were obtained, we measured the quantity of material taken out, the temperature, the conductivity, and then we sent these to an analytical laboratory and tested them for the heavy metal constituents. Lysimeter A, as I mentioned earlier, is under the limestone, and lysimeter B is beneath the blended materials. You see that initially we had some readings in all of our heavy metals on the first go-around of sampling. But after the second sampling, the barium, cadmium, and chromium numbers all dropped down to non-detect limits, but the arsenic levels still remained high. It should be mentioned that in Ohio that arsenic is a naturally occurring background material in our soils and groundwater. So it's pretty typical to see arsenic show up in places that normally a person wouldn't think you'd see them. Studies by the University of Wisconsin on recycled concrete aggregates compared to natural aggregates shows the same trend of readings. Initially, it appears that the arsenic levels were higher in the recycled aggregate blend as opposed to the limestone, and that over time the limestone cleaned up faster, and we believe that this is primarily due to the amount of water that was collected. We had more water flowing through the limestone base than through the blended foundry sand concrete base. It's just a point of noting here that the pH content on the limestone materials are all around 7 is where you'd expect them to be. The pH on the recycled concrete foundry sand is up around 12 to 13. This is due to the concrete material in this blend, and this high pH is typically what you would expect for concrete materials. So in summary, falling weight deflectometer data indicates that the recycled concrete aggregate foundry sand blend for the base course functions as well, or maybe even slightly better than the standard O.304 crushed limestone when placed over the same subgrade materials. Refining of the recycled concrete foundry sand gradation by more controlled processing by better crushing and blending methods may produce an even better base material with further study. And finally, the analytical test results for metals are very similar for both materials, but are higher for the recycled concrete foundry sand base. Again, we believe this is really due to the amount of water that actually permeated through the base and was collected. With that, I conclude the presentation and now open for discussion or questions. The other question here was there data on the raw analyticals for the foundry sand without other materials. We did not run initial analyticals on the constituents, but there's pretty well documented for the source of this foundry sand what those constituents are. Question is, what is the percent foundry sand used in the recycled concrete foundry sand mix? It's approximately 12% foundry sand, with the rest being recycled concrete. Again, with the better crushing and blending methods, we believe that we can increase the percent foundry sand, possibly as much as doubling in the amount with a better processing of the concrete.
Other questions?
I see one other one here about the mass of the arsenic released from the two substates, and no, the answer is no, we didn't compute this. The state of question is, how do we plan to communicate these results to the state DOTs? The state of Ohio here is very interested in this current study, so we were sharing this information with them. If you, there was a study done fairly recently with all the different states questioning which ones used recycled concrete in their roadway projects, and if you look at a map of the U.S., Ohio is surrounded by states that use it. At this present time, the state of Ohio does not use it as an approved material, except I do believe they do it on a case-by-case basis.
Another follow-up to that would be this information is going to be maintained on AFS's website for corporate members and then those that are using SharePoint. Looks like we had another question, John, came in. Does the additive that the metal casting facility used make a difference? And I'm assuming that question refers to what binder systems. And I believe this binder system, this was a green sand, is that correct, John? Clay bonded system?
Yes. I think, Mike, you could probably speak to that better than I can.
Yeah, the sand that was used in the system is a green sand. For those of you who are not familiar with Foundry sands, that would be a clay bonded system as compared to a chemically bonded sand, usually used to make molds. Looks like we have another question. Was the arsenic in the Foundry sand, or maybe was there arsenic in the Foundry sand? I think the answer is there was not a separate set of analytical taken for this particular sand. The data is showing what the data is showing. But I believe through John's experience, and I would certainly say that's not something we typically see in high amounts in Foundry sand.
Yeah, and I would concur with that, Mike. It's just not a metal that pops into my mind when I think of the Foundry sands that were used, but I have seen it in, like again, in limestone base, in recycled concrete material. You also see a little bit of it in, if you get into fly ash, which is a pretty common material around our area, that it has some very slight arsenic levels in it on the leachates, but again, they're pretty small. In Ohio, there is arsenic in the groundwater and also in naturally occurring in the soil in our area.
Any other questions? Last call on questions. Okay, with that, we'd like to thank you for joining us this afternoon on